many of these with a question on the forum. The question being, if we use software interrupts to count pulses, how fast can we count? Now, I'm sure if you're familiar with counting pulses, you'll immediately say that a timer should be used rather than doing it with software. But this is an excellent opportunity to look at how fast can we do it and what factors can help us get faster, better interrupt response. So to investigate this, I have a Teensy here, and I have on this wire connected to a frequency counter, and this wire here is connected to a function generator. We'll just be feeding in a square wave. We can get closer and take a look at this. So when we do these tests, I'm just gonna connect this wire right here so that we can put pulses in. So this is the code that I wrote to do this test. It's very simple. We're going to use attach interrupt to run this pulse function. The pulse function just increments a count, and then the loop code down here is just going to when the count is different than the last time we printed it, we're just going to print the number and make sure that we don't print too quickly to overload the Arduino serial monitor. And that's it. So let's upload this to the Teensy, and we're going to be doing this upload every time to set this back to 0. So if we come over here and look at the frequency counter, I already have this test set up here to 100 kilohertz, and we have the frequency counter set to 0. So let's hope this works. When I just connect this here, we should see the numbers go up on both, and when I let it go, hopefully they end at the same number, or hopefully within 1. So I see that we ended up, yep, at the same number, 330, off by a few, but pretty close. So let's try increasing this, and if we come over here to the frequency on the waveform, square wave frequency, and if we try a much faster frequency, let's try 600 kilohertz. That's quite a bit quicker. We'll zero the frequency counter, zero the Arduino just by uploading again. Now this probably will lose counts. This is probably too quick. Let's give it a try. And let's let it go for a moment. And there we ended up at 3710 at the end. Yep, and we can see here that we got a much smaller count in the serial monitor, and that's because this missed interrupts. It was doing other work and not able to keep up with the count. And I'll explain why in a moment, but let's take a look at this now. This is the code here, and if I bring in this line here, this line says to set the priority of the interrupt. And unfortunately, this isn't a very Arduino-like API. We have to look up pin 3 and see that pin 3 is on port A. And then these interrupt numbers are between 0 to 255, and the smaller the number, the higher the priority. So what these interrupt priorities do is, with normal interrupts, what would happen is when we have the interrupts coming in rapidly and we're servicing them to increment the count, occasionally we need to do an interrupt to communicate with the serial monitor, or we need to do an interrupt for Arduino's timekeeping to update the millis count. And when those interrupts happen, we can't service the pulses. What this does is, in these ARM processors, there is what's called nested interrupt priorities, where we can allow an interrupt to interrupt another interrupt. It's all done by hardware. All we have to do is set up the priorities. So when we set the priority of the pin interrupt to this number 0, the maximum right here, what that means is that these interrupts will be able to interrupt the communication interrupt, and we should get much more reliable servicing of the interrupts. So let's give that a try here. We'll with this code in there, we'll just upload again to the board. We'll come over here and set the frequency counter to 0. We're at 600 again now. And let's do another quick test at 600. And now, in a moment, we should stop. And what do we see? 2, 1. Yep, we see that the numbers matched. So this allows much better counting, all by just having this interrupt priority set correctly. Now, something that we'll see as a consequence of this, if we want to figure out how fast we can go, is if I connect this again, so now we're counting again. If I come over here and I just increase the frequency, hopefully you'll be able to see this on the screen. As I turn this number up, when I get to a frequency that is too fast, we'll see the numbers in the serial monitor stop. And there they are. We went, was it 1.5? Come back down a little. Okay, there they're going at 1.4 megahertz. And at 1.5 megahertz, what's happening is the processor is just not fast enough to execute 1.5 million interrupts per second. And so and because it's the highest priority, nothing else is getting to run on the processor. No communication happens. So if we turn this down, we'll just try coming down a little bit, and we can see that it's just barely starting to communicate. Just barely. See, we can turn this up and it's having trouble. So let's try coming down a ways to be conservative. Let's try 1.3 megahertz. Let's try disconnecting the signal, and then we'll zero the count here, and we'll test to see if we can really get 1.3 megahertz to work. This worked earlier before I turned on the camera. Oh, and I sure hope it works again now. Let's give it a quick try here. Put the cursor there. Okay, and in a moment I'll take it off here, and hopefully we get the same number on both. And we're pretty close, but not quite. Just a few less on the Arduino side. Let's try coming down. Let's try coming down to 1.25 megahertz. And try this one more time. Zero the count here. Upload. We got very, very close. Okay, we're shooting for getting the same number on both. Here we go. Going up, counting. And here we go. It looks like we got the same number on both. We could get a little bit of contact or mechanical chatter bounce on this, but could also explain these discrepancies when we're within just a couple counts. But there it is. So we can actually, it looks like, execute 1.25 million, 1.25 million interrupts per second is the most interrupts that we can do on the Teensy 3.2. Let's try this same experiment really quickly. If we just swap out the Teensy 3.2 here and put in the faster Teensy 3.6 board. This is one that I keep on my desk with these taller pins so I can easily put it into sockets that had projects made for the 3.2. If I come over here and select the Teensy 3.6 board, and then we can see that the CPU speed here will be 180 megahertz. So quite a bit faster on this board. Same exact code. We'll upload it here. And then once it's uploaded, we'll set the counter to 0. And let's try going to 2.5. Let's try 2.55 megahertz. Oh, I hope this works again. This works approximately what it did before. If I touch this, hopefully we'll get the same number after it counts for a moment. 2.5 million counts per second. And did we end up with the same number? 105.9. Yep, we came very, very close. The Arduino serial monitor prints faster if I put the cursor in. Let's try a few more counts and make sure this really is counting. Why is the computer screen isn't refreshing? I think my video capture, screen capture, is slowing it down a little on the screen. But there we've counted a whole lot of counts. We end at 20340, 20340. So there it is. That is how we can count and prioritize the interrupt to get the maximum CPU priority. So it takes precedence over all the others and interrupts the others. It lets us get the maximum possible counting. I mentioned earlier, though, that this isn't the best way to do the count. In just a moment, let's look at how we would use hardware to actually be able to count much, much faster. But if we want to do software interrupts to respond to events, hopefully doing something a little bit more interesting than just counting, this is the way. This is the key ingredient here to be able to set the priority of the interrupt so that it takes precedence over the communication interrupts, allows the best possible counting speed. Okay, so to finish this up, here I have the Teensy 3.6 connected, and we've got the two wires connected to the breadboard. On this final test, we're going to do things a little bit differently. I'm going to use the function generator to turn the signal on and off, because it turns out that this is so sensitive and able to count so quickly that the mechanical chatter of putting this wire in and out of the breadboard leads to quite a bit of error. So here in Arduino, this would be the way that you would, if you wanted to really count the number of pulses at maximum possible speed, you would use the frequency count library. This code is very simple. It just every time the frequency count library gives us a count, which will be every 100 milliseconds due to this line here, we're just going to read the number of counts that we saw, add them to a total, and print the total out here if it's different than the previous one. Very, very simple. Let's upload this to the board. It should do pretty much what we just saw with the interrupts on each signal, except we're not actually, we're only interrupting 100 times a second. And so here we come over to this. I've got this set to the same number we saw here, 2.55 megahertz. And now this time we're configured on the channel button, and if I just turn this on, we should see the numbers happen. And you can see in the serial monitor they're only printing 10 times a second. And when I turn this off, I hope these end up at the same number. Here we go. And we got pretty close, within a couple. And I'm not sure why we have a discrepancy of two counts. We ended up in 1164 over there and 1162. But we can see it's working. So let's come over here to the frequency number, and let's see if I go to waveform, square wave. Let's turn this up as high as it goes. So let's just keep turning this number until I could type this in. This function generator will go up to 30 megahertz, and on the square wave. And then if we could just leave this here, leave that there. Let's actually let's set this back to 0 again, and let's set the Arduino side back to 0. So we're doing one test the same way we did all the other tests. Now let's see this count at 30 megahertz. Again, I hope this works. Here we go. We're going to take the channel and turn it on. You can see that number's counting very quickly on the frequency counter. And when we turn it off, we sure hope these end up at the same number. And no, we didn't. Oh, and we got more counts over on the 1675 there, and 19. We ended up with more counts over here, which is a little bit mysterious. Again, this is so sensitive, and I believe this frequency counter. Let's try it one more time. We'll go over here to the waveform. Let's try turning it on. This is so very sensitive. When I tried these tests earlier off camera, there was a tremendous amount of sensitivity to the slightest mechanical chatter. And again, we're not getting perfect agreement over here, and we're getting very, very close. We ended at 463 over there, and on this one 307. I wonder if my BK Precision, I wonder if it's not doing. That's very interesting. Where actually it appears like this might be losing some of the counts. It's not what I would have expected. I would have hoped that this thing. But let's try bringing this down to only 20 megahertz. I guess I'm going to have to. It's a little touchy on the 20 megahertz, and then we'll try zeroing this again. Come over here to the Arduino and zero out. Start the sketch again. Let's try one more test here at only 20 megahertz counting, and we'll come over here and turn the waveform on. There, it's counting up, and let's try turning it off. And there we ended at 18143, and oh, and not the same here. I'm at a loss to say why this isn't agreeing, and I'm a little bit perturbed about that. Let's try one more test again. Let's try zeroing this out. Come back to the waveform, square wave, frequency of only 10 megahertz, frequency of 10, oops, I see what I did, 10 megahertz. Slight mistake there. Okay, let's upload, reset the Arduino one more time. I must confess I didn't practice this faster than 2.5 megahertz before I turned the camera on. This is pretty typical of how electronics often goes. Alright, we're at 0 there. Let's try one more test. And where we've counted, there we ended up at 53100. Oh, and here we're at 53097, so we're agreeing within a couple counts. It might be that the totalization on this BK Precision might not be able to actually work at that 20 or 30 megahertz. I know for sure that the Teensy counts up to 30 megahertz. So there you have it. If you're going to actually count, if you just want to count the total number of pulses, the software, running one interrupt per every single pulse is obviously not the most efficient way to do it. You can easily count 30 megahertz, and this might work up into the 65 megahertz if the other testing on the frequency count library is any indication. So I hope you liked this video. Sorry this last part went a little bit long. I didn't actually practice every part of this before turning the camera on. These videos I'm doing mostly when I see messages like this one over here in the forum. So if you have a question that you'd like me to pursue and to explore, such as how using this counting principle, how fast can we go? Please ask on the forum, and I might make a video out of it. And if you'd like to see these videos as I do them, please subscribe to the channel. Thanks for watching.